So the other day I was shopping for some headlamps for my car, and I thought it would be really funny to put some of those super expensive xenon headlamps into my 11-year-old car. I did a little bit of research, and it actually turns out that those headlamps are not compatible with my car. But that's okay, because they're really expensive. But why are they so expensive?
I must say, I think that's a perfectly reasonable question.
Of course it's an excellent question. How does a person answer why something happens?
Okay, well, one of the reasons it might be so expensive is there's not a lot of it in the Earth's atmosphere. But why is there not a lot of it in the Earth's atmosphere? Well, in order to answer that question, we have to look at a bigger picture and see what happens when stars die. And that's the story that I want to tell you today on Once Upon a Spacetime. Once upon a spacetime, there were two gas clouds stuck in an epic battle between gravity, trying to pull them in and make them collapse in on themselves, and radiation pressure, trying to push them out. Eventually, one day, gravity advanced enough that hydrogen atoms in the center were able to fuse to form helium. And at this point, our two stars were born, each about 15 times the mass of the sun. As the stars grew up, they went through their hydrogen, turning it into helium, each time releasing a little mini explosion. Throughout their lives, they were stuck in this battle between gravity and radiation pressure from the explosions. But so long as they were able to generate enough outward pressure, they were able to keep from collapsing in on themselves, and were in hydrostatic equilibrium. But as the hydrogen gets used up, gravity starts to take over, causing the cores to contract. And when this happens, the temperature increases, and even heavier things can form. Carbon, neon, silicon, heavier and heavier each time. And at each step, whatever gets made gets used up as fuel, faster and faster each time until it reaches iron. And at this point, fusion can no longer occur. And this marks the death of the star. With the end of fusion, there's no longer enough support against gravity, and the stars start to collapse from the inside out. The cores get so hot and dense that atoms get stripped away, and neutrinos are produced, carrying energy away. The cores become as dense as the nuclei of atoms. Material from further out in the star falls in and bounces off of this solid core, pushing what still remained further out in the star out in one of the largest and most energetic explosions in the universe. The stars have gone supernova, and all in a fraction of a second. What remained were stellar corpses, made up of material tightly packed together at nuclear density, held prisoner by the force of gravity. Imagine, if you will, the mass of more than 300,000 Earths wrapped up together in a tight little ball about as wide as a city. Billions of years later, these two neutron stars would meet each other again, brought together by the same force that created them, gravity. They danced around each other, spinning faster and faster each time until eventually they crashed together. Now I want to take you even deeper into these neutron star mergers and follow the story of characters tinier even than the atomic scale. When neutrons and protons are together, they form an atomic nucleus. And just like the hydrogen nuclei that formed our stars in the beginning, these nuclei interact with their worlds in different ways. They can add neutrons and protons and get bigger, or they can decay and become smaller. But one of their main goals is to be stable and live in the valley of stability. On one side of the valley, nuclei have too many protons and are proton-rich. On the other side of the valley, nuclei have too many neutrons and are neutron-rich. For light nuclei, living in the valley usually means having about the same number of neutrons and protons. But in the upper regions of the valley, this tends to shift, and stable nuclei tend to have more neutrons. A single neutron is only stable for about 15 minutes, and at that time, it decays into a proton, electron, and anti-electron neutrino. And in a similar way, a nucleus that has too many neutrons can get to the valley by turning some of its neutrons into protons. And the further away from the valley this nucleus is, the faster it's going to do this. But there once was a proton that found itself surrounded by neutrons caught in the outflows of a neutron star merger. The neutrons latched onto the proton, forming a heavier and heavier nucleus, and doing this so fast that it forced the proton to stray far from the valley of stability. But for every couple of neutrons that latched onto the proton, it was able to turn some of those neutrons into protons. Thus the nucleus, now no longer a single proton, but still very neutron-rich, was able to grow into heavier and heavier elements. But every step closer to stability meant more steps further away, keeping it from the valley, as the nucleus grew to more and more neutron-rich. As the seconds went on, turning into minutes, the onslaught of neutrons lessened. But by this time, the nucleus was already quite heavy, It had become an actinide. And at this point, a new path opened up. The nucleus could fission, undoing what its ancestors had done in the stars billions of years earlier. It could split into two parts. Then, from there, since the free attacking neutrons from earlier were now locked up in other nuclei or were spread out enough, the daughter products from this fission could find their way back to the valley easier than they could before. Thus, our actinide nucleus was able to split into two, and those two daughter products were able to decay their way back into the valley, and they were able to form the region where xenon lived. So currently scientists are trying to understand all of the different complicated and messy parts that go into actually making this process happen. But for the purposes of our question, it seems like we actually don't need that much. We need a couple of stars to live their lives and then die in some of the most explosive energetic events in the universe. We need a couple billion years, and we need a whole lot of neutrons. That's only like 3 things. So I know before I said that those xenon headlamps seemed kind of expensive, but in retrospect, they don't actually seem that bad.